We were interested in this nonlinear PDE driven by a rough right-hand side, for instance, white noise. I told you, and in principle now we would also have the tools to really pin that down. I told you that there is a problem because even in the linear case, the phi is so rough that it's not a function anymore, so phi cubed doesn't make a sense. So as it stands, this equation doesn't have a sense. So then we said, okay, why don't we just regularize the noise? Then everything can be written down and is smooth. Any solution will be smooth. And but then we still have the problem that's in a certain sense cheating, because we still have the problem that as rho goes to 0, the solution manifold as such doesn't converge. And I said we have to introduce a counter term into this equation, and in a certain sense there is a direct balance or interaction between these two phenomena. As you let the regularization go to 0, the counter term has to blow up in such a way that the solutions converge. And then eventually we kind of, it was convenient to relax this a little bit by saying we look at all the functions phi which satisfy this, which are of this form. That's our solution manifold. And then we introduced this parametrization of the solution manifold, and we introduced coordinates, and which allowed us to completely algebraize this problem, to convert it into a term-by-term problem, giving rise to the c and to the pi, and the pi minus, and eventually also the gamma, because these things are allowed to acquire a base point dependence. So we have all this structure, and I tried to kind of convince you that there was a unique way of defining these objects. They all depend on rho. In particular, this one depends on rho and is expected to blow up. But hopefully, these objects don't blow up. Well, that's the main claim. So the claim is that no blow up as rho goes to 0 of this part. And the main challenge in this is still around. I mean, we haven't done anything to solve the challenge. We just rephrased things because of this relationship between pi and pi minus, which I'm going to write down once more. 1 plus 2 plus 3 is equal to pi beta 1, pi beta 2, pi beta 3. Plus the sum over beta 1 plus beta 2 is equal to beta, c beta 1, pi beta 2, and then still a noise, psi delta konica beta 0. So that was the relationship, and I told you last time that this one is in a certain sense unstable, non-robust. As rho goes to 0. Of course, as rho is positive, we can write it down because everything is smooth, and but it's not robust as rho goes to 0 for two reasons. On the one hand, this blows up, so this term becomes an infinity. And on the other hand, this term, well, we encounter very much the same problem we had here in the beginning, that as rho goes to 0, the pi's, and we'll look at an example in a second, the pi's themselves cease to be functions and just kind of will be just distributions, most of them just of the negative order alpha. And so again, we have the problem that for distributions, I cannot take for genuine distributions, I cannot give a good sense to a product. So this is also an infinity. And And in a certain sense, that's the issue, when writing this down and passing to the limit, you get a cancellation, or there are two infinities which emerge, which means, from any practical point of view, this is a bad representation, right? Like in numerical analysis, if you have a kind of something where you have huge cancellations, that's a very unrobust, unstable representation. So what we do, what we seek is seek a robust representation. And the main message of today, and in a certain sense of this work, is that you get this robust representation on the level of the Malliavin derivative. So while this relationship from pi to pi minus is bad, we will see that we can do it well on the level of the Malliavin derivative. So that's the I would say the main insight of what I'm telling you, that this thing which is which is kind of which cannot be redeemed becomes reasonable. This relationship becomes reasonable on the level of the Malliavin derivative. But it's a bit subtle, and that's what I want to continue to tell you. That so there are the obvious. So I mean, last time I mentioned that working with the Malliavin derivative in this somewhat unusual way. So typically, you know better than I, probably, or most of you, or some of you know better than I, that the Malliavin derivative Malliavin calculus is typically used to prove that certain densities are regular. This is not at all how we're using it here. So we're using it in a kind of in a different way in order to bound rather moments of random variables, algebraic moments of random variables, via some kind of spectral gap estimate eventually. But we actually use it in a more conceptual way, in this way. And in principle, it's very natural to use the Malliavin derivative because there are these three pluses, three advantages. The first advantage is that because we postulated that this counter term is deterministic, which translates into the postulate that these constants here are deterministic, they're killed by the Malliavin derivative. So that's obviously something which points in the right direction. The second thing is that, so we'll be in particular interested in the Malliavin derivative, in this directional Malliavin derivative of random variables, which consist of taking a component of this pi minus, which is in a certain sense the most interesting object, which in the limit is just a distribution. So we convolve it on some small scale r and we evaluate it, let's say at x, not at 0. And we consider the Malliavin derivative. And the Malliavin derivative as a noise derivative kind of controls fluctuations. Or eventually it will control the variance. And that complements the fact that the expectation of these things, at least if r goes to infinity, is controlled by our scheme. That was the way how to choose the c's. So let me just say by BPHZ. So in that sense, working, and let me put the minus sign here so that we really have the same random variable. So taking this Malliavin calculus in a very natural way complements the strategy, the physicist's strategy of choosing these constants. Namely, they choose the constants in such a way as to annihilate certain expectations, certain means. So that's clearly a plus. And the last plus is that you're replacing something which in a certain sense is on a scale of -3 plus s by an element of the Caron-Martin space, and you gain 3 derivatives. So, those are the 3 obvious advantages of using Malliavin calculus in this business. Okay, but now I want to tell you that it's not that simple. So let's consider. So not that simple. Consider. So let's take the Malliavin derivative of this relationship. So by Leibniz rule, we get del pi minus is equal to 3 times z3 pi squared plus c times del pi plus del psi times 1. And of course we have that L del pi is equal to del pi minus plus some analytic function. That's what we get from just applying the Malliavin derivative to the definition of the model. And we're using, of course, that the Malliavin derivative commutes with the space-time derivatives because partial derivatives do commute. So we end up with, if I can combine these 2 things, we end up with a PDE for the Malliavin derivative, or a system of a hierarchy of PDEs for the Malliavin derivative, which can be combined into this line. So in a certain sense, it's at first, I mean, structurally it's nice because here you have the model itself, and then the Malliavin derivative now solves a linear equation. That's not surprising because taking a derivative linearizes the problem, so it's not surprising that you would end up with a linear equation. So that's nice. But let's look at 3 components of this. So let's look at the components. I mean, in a certain sense, the easiest components when beta is the 0 multi-index, when it's delta 3 and 2 times delta 3. And let me spell out what you get. And I want to convince, yes?
Why is the analytic function survived to the Malliavin calculus?
Those are random analytic functions, so because they depend on the realization. That's my, in a certain sense, my understanding here. When I write this, I mean random analytic. And again, I had a discussion with one of you yesterday. I'm in a certain sense, I'm relaxing the condition of being a solution by adding this term here. I'm saying, I'm in a certain sense, I'm being more ambitious, right? I'm saying instead of just keeping my solution manifold in track, I'm really saying something about a much larger space. Namely, solution modulo is a very smooth function, and the smoothest function is an analytic function. In fact, that will be, as an intuition, will be important in a second. More questions? Okay, so let's look at these. Three cases. Just to get an idea that it's not an easy fix. And one needs to develop kind of some more geometric understanding to really make it into a fix. So what I want to convince you of is that this component is no problem at all. This component, you're lucky, it works. And this component, that's the simplest one where you see that it's not, not that easy. So there is a good one. So good is beta equal to 0. So I'm just taking the beta equal to 0 component of this equation. Then this entire first term drops out because of this Z3. It doesn't have a beta equal to 0 component. and because C just starts at Z3 and Z3 square, this entire term drops out, and the only term which survives is this one and plus analytic. In fact, we know that if I take the component beta here, then we said we want this to be a polynomial of degree less or equal to beta minus 2. So this thing is actually not there. So what we have is just that L pi 0 is equal to del xi. Now, very simple. And since the right-hand side is in the as an element of the Cameron-Martin space, in particular, is in this slightly positive Sobolev space, we get that by linear regularity theory that this thing must be 2 digits better. So this is already pretty smooth on the Sobolev scale. It has somewhere between 2 and 3 derivatives. Remember that S, we're now working in this range where S is between 0 and 1. So here you see the first instance of this beneficial thing. While the pi 0 was not a function, just a distribution in the limit when rho goes to 0, its Malliavin derivative, in fact, is a nice Sobolev function, somewhere between H2 and H3. So that's nice. Now let's look at del 3, and I say that's still good. So what happens here? Now, of course, this term now goes away. The noise is gone. The polynomial is still not there. And now this term, remember that the way we took products, pi prime, beta was beta, okay, pi 1, pi 2. Beta 1 plus beta 2 is equal to pi. Beta pi 1, pi 1, 2, beta 2. So I have to split the del 3 into 2 parts. There's only 2 ways of doing that. 0 del 3, but that will vanish because this vanishes. The 0 component is 0. So what survives is if the del 3 component falls onto this and the 0 component on this. So you get 3 times pi 0 squared plus C0 times C1 times del pi 0 plus nothing. So that's the interpretation of this. That's the interpretation of this component. And so now this is still nice because this here is actually a friend. This is something we know because this is nothing else than pi minus for the index del 3 plus del 0. And in fact, we know that this has a certain regularity. So the regularity of this one is, is essentially, and I'm giving this justification in the notes, the regularity of this one here is the homogeneity of this index, minus 2. The minus 2 comes from the minus sign. And the homogeneity of this index is 2s. That's something I already wrote down at some point. So, so the regularity of this factor here is 2s minus 2. And this one here, is h dot 2 plus s. And now you see that this is still okay because the sum of the 2 regularities, which is for the first factor 2s minus 2, and for the second factor 2 plus s, is equal to 3s, and that's positive. And perhaps you have, from rough path theory or kind of stochastic integrals or Young integrals, that such products between a function and something which is just a distribution, they're okay if the regularity of the function compensates the irregularity of the distribution. If the order of the regularity of the function is higher than the irregularity of the distribution, which means these two numbers have to be, the sum of these two numbers has to be positive, and that's the case. It's in a certain sense barely the case, but it is the case. So in principle, this line is still okay. So can be interpreted in a robust way. So we could pass, so let me say, is robust, could pass to the limit rho going to 0 here. But of course, that's very when you take a product between a smooth function and a rough distribution, the regularity of the product is always dominated by the worst factor. Easy thought experiment, take this function to be equal to 1, then it's very obvious that the regularity of the product could never be better than this one. So we know that this product here is not better than h dot 2s minus 2, right? So that means the solution of this equation will be not better than h dot 2s. Yeah? And that's kind of bad enough to create a problem on the next level, because on the next level, what we get is 2 times del 3 0. So now that's gone, that's still gone. But here we get now 2 out of the 3 contributions do survive. And there is the first contribution, which looks like this one here, at least when it comes to the first factor. C1 times del pi 0, but then there is a second factor, which is 6 times, let me look it up. Six times P0 times P del 3 plus C2 times del pi D2. Is that correct? I know, and here it's del 3 and here it's 0. Okay. That's what you get. So as usual, and this is why in the end you want to avoid that. As usual, these formulas get more and more complex as you go higher with your multi-index. So therefore, it's so important in this field to kind of develop a certain automatic way of thinking about these things. So you see this already here, that things get more complicated, and the next one you wouldn't like to write down anymore. But now we have a problem, right? Because this thing here has still regularity of the order, let me say, C 2s minus 2. Whereas this one here, we just have learned, is not better than h dot 2s. And now the sum of these two exponents, 4s minus 2, typically will be negative, because we're thinking of s being very close to 0. That's the interesting case. So this product here is singular. Oops, that's gone. Is singular as rho goes to 0 for s less than 1/4 or less or equal to 1/4. And we're mostly interested in s being just slightly positive. Yeah, that makes it, get as close as possible to white noise. And so here we have a problem. Now, what about this term? So we should have a problem in this term too, because if we just would have a problem in this term and no problem in this term, then we would have a problem in this term, and that would kind of kill the approach. So we should somehow see that this term is also problematic, that we can't play the same trick as here. And indeed, the reason for this is that this is not quite pi minus 2 times del 3 plus del 0. There are a couple of more terms in this one here. And therefore, we cannot say it's conceivable that also, and we hope for this, that also this one is bad, despite the fact that this is still very good, right? This still has almost 3 derivatives. So if that were an identity, then we would be into problems, because then this product would be good, whereas we convinced ourselves that this is bad, and then this would be bad, and then our strategy would be doomed. So also on the third term, you already see the same principle, that this is still a bad representation. You still have kind of 2 infinities. You still want to fight against, you still haven't found the right representation. Okay? More questions? Other questions? Okay, so now in order to cope with this problem, that while at first it looks like taking the Malliavin derivative has only advantages and is very natural, and indeed it is, if you start implementing it, you run into the difficulty that it doesn't yet solve the problem. So because of this, we need to step back a bit, and I have to kind of appeal again to your geometrical intuition, because that gives you the right idea of what to do now. And so in fact, you get the right idea by thinking of the I have to look up the chapter 4, section 4, by thinking of the tangent manifold, tangent space. To the solution manifold. So at first, why is it not outrageous now to think about the tangent manifold? Well, taking the Malliavin derivative is taking a derivative. So of a solution. So in a certain sense, it's naturally to think about that, to think about the object which you get as a tangent vector to the manifold of solutions. And but there's a slight twist which I want to explain. So forget about the Malliavin derivative for a moment, and let's just think about the tangent manifold. So let me momentarily introduce this notation of all phi at fixed lambda. So phi which satisfy phi which L phi is equal to lambda phi cube plus h of rho phi plus psi rho at fixed lambda and fixed psi. So because we fixed the psi, this is not something we can instantly apply to the Malliavin derivative. But so how would you approach the issue of, so this is kind of m lambda, and here you have a configuration phi. How would you approach the understanding of a tangent vector? You would give yourself a curve, phi of t. So fix a phi in this manifold. Consider a curve which passes through this manifold, which at time t equal to 0 agrees with your given phi. And then of course, phi dot, which is the time derivative at time equal to 0, phi of t, should be considered a tangent vector. And differential geometers would write. So you have this manifold. You take your tangent space in the point phi, and that would be an element of the tangent vector. And by varying the curve, you would get every tangent vector in this manifold. Right? That's the intuitive. That's the intuitive thinking. So that defines kind of the tangent plane to this manifold. And now, of course, we learned something because if we, for a moment, plug in the t here, and then we take the t derivative and evaluate it at 0, we learn that tangent vectors, phi dot, are characterized by the linearized equation. Plus, I forgot the analytic function, sorry. Plus analytic. So that's a nice observation, which is a little bit reminiscent of one of the talks yesterday from the gentleman from Mexico, that if you, here also the noise drops out, right? So by taking a tangent, by looking at a tangent vector, the noise is gone because the noise doesn't depend on t, so when you derive it, it goes away. But still the equation is noisy because this coefficient contains the noisy solution. So it's you're still, in a certain sense, in a noisy environment, but the worst part of the noise, in a certain sense, is gone. So now what does that mean in terms of the parametrization of our parametrization by P? So what does that mean on the level of the parametrization lambda p goes to phi? Okay, so that means we now want to think of a phi, which is, comes from a, so hence we consider a phi which can be given in the way we like. So z beta lambda p pi beta. And we ask the question, do we also get a nice representation of pi dot? And that's almost tautological. Because what do we have to do? So we have here our manifold with our curve. We have our parameter space. So this is phi, this is p. So the analytic functions, this curve up here, which we use to kind of define the tangent vector, of course it lifts or it projects down to a curve down here. And so we have now this identity. And now what we do is we apply our tangential derivative operator to this identity. So what do we get? Very formally, we get phi dot is equal to the sum over beta, and then the derivative of this guy, and I will immediately use the chain rule. So there is Zn derivative of Z beta times lambda, or evaluated at lambda times p. And then there is an inner derivative, which I call little pi n dot times pi beta. And for some pi beta dot, sorry, pi n dot, which are just real numbers. So, and this here is just something very intuitive. So where dZn is taking kind of, we have these infinitely many variables, and we take a derivative in direction of the Zn variable. So, and we apply it to our monomial Z beta. So what do we get? Well, that's kind of algebra or analysis. Beta evaluated at n times Z beta minus del n. This is how you take a partial derivative of a monomial with respect to one of its variables. And this is what this is. But in fact, I will tell you in a second that this operator here also has a nice algebraic, you can completely algebraically understand as something what the people in differential geometry or in algebra call a derivation. Okay, so this is almost tautological. So we learned that because we insisted on really parametrizing the entire solution manifold, now that comes to our advantage because we have a parametrization of the tangent space. So here we know that we can kind of represent any tangent vector, phi dot, by a bunch of numbers. Questions so far? Yes?
The parameter t is the same as the x0?
No. This is why I called this one x0. So this is, like in differential geometry, you want to parameterize a curve by some parameter. I called it now t. Perhaps you prefer s, but s is already used. I could use tau. It's just a different name of a variable by which I parameterize this curve. More questions? Okay, so that's what we're doing now. And now in the next step, I want to algebraize this, like we did so many times already. And already with an eye on this equation here, I want to consider a pi dot, which is an element of formal power series with coefficients in random space-time functions, which solves this equation, because that's exactly the form up to this term we have over there. So I now want to develop an understanding of kind of solutions of this equation with help of this insight. And the claim is, so still informal, is that I can write this pi dot as a sum over n of numbers, or in this case it's already more than just numbers, little pi superscript n dzn capital pi for some pi n's, which now are formal power series, with in fact random real coefficients. So so what's informal here, that I'm still informally taking a sum over infinitely many of these n's. What's not informal is this derivative. We'll say something with respect to this. And in fact, before I tell you how to derive this from here, we need it to to really find the good representative for the good representation for the Malliavin derivative, we need it for general base point. So let me see how I want to phrase this. And let me logically turn it around and make it into a kind of rigorous statement this way. So if pi, and I should put the dot here, that's the same dot as here. So if I'm given pi dot xn's, which are in this space and where the sequence is finite. So it breaks up after some finite n's. And consider a capital pi dot, which is defined in almost this way, namely the sum over n little pi dot xn, gamma x star del zn of pi x, and that's well defined as an element in this space. Then this implies the equation up there. L pi dot is equal to 3z3 pi squared plus c pi dot plus analytic. So those are kind of the three claims I want to kind of explain in this section. So the first one I did. So we get from this manifold perspective, we get a representation of every tangent vector. The second one I didn't. That's still informal. That if we have a solution of such a kind of hierarchy of equations, then I can represent it in terms of the pi, in terms of our model pi, like this. But in fact, this is always with respect to the base point 0, and I need something where that will become apparent soon. I need something where I have a flexible base point x, and then the representation changes a bit, and the difference is that this thing here comes in, and if you set x equal to 0, this here turns into that. Because for x equal to 0, our transformation is just the identity because we're not transforming any base point. So that's kind of, this is a special case of this. But here I'm turning the logic around. I'm saying, let's suppose I have such a representation, then I get the equation. And this is something we can check. So let me take a quiz, or let me take a poll. So I can give you the informal argument why this here is just a one-to-one translation of that. Or I can give you the formal argument, the rigorous argument, why this implies this. Who wants to see the informal argument? Who wants to see the formal argument? That's a couple of more people. So, but I mean, both are in the notes. So let's look at the this rigorous statement. So let me give you the argument. So the first claim is by linearity. So since this here is an object which does not depend on the active space variable, which is somewhere suppressed and sitting here, let me call it y. Since the only dependence on the active space-time variable y is over here, and this is not y-dependent, this is not y-dependent, I can say by linearity it's enough to, and since this here is a linear equation, it's enough to consider the case where pi dot just consists of one of these terms. Right? So I have to convince you that if I take my model, which we constructed in the past, at some base point x, I apply this operator here, which is an operator which only acts on the formal variables. Then I apply this endomorphism, which also essentially only acts on the formal variables. Then I get an object, so all of this takes place in this space X, which we have been looking at. Then I get an object which, if I apply now something which acts on space-time, like our differential operator L, I get this equation, right? That's what I have to do. So let's do that. So, okay, so apply the space-time operator. So again, since this here doesn't act on the space-time variables, but it just acts on the somehow dummy variables, and this acts just on the dummy variables, the L commutes with this object. So it commutes with gamma star x and d zn. So what we get is that L pi dot is equal to gamma star x dzn L pi x. But by construction of our model, we know what L pi x is. That's just Z3 pi x cubed plus c times pi x plus psi convolved 1. Plus an affine function, plus analytic. And of course, this here doesn't change the fact that something is space-time analytic. So what we get is this here plus something analytic. So I just want to convince you that, with this, despite the fact that this is a kind of blown up structure, you can do calculus in a rigorous way with this. So now we're here, and now one has to realize that this turns into that. So that's not so difficult because this del n operator, let me erase this, is a derivation So del Zn is a well-defined endomorphism of this power series space. And in fact, this is what people call a derivation, which means it satisfies Leibniz rule. By which I mean that if you apply del Zn to the product of pi and pi prime, you get del Zn applied to pi times pi prime times pi plus pi times del Zn applied to pi prime for any pi prime, which are elements of this algebra. And of course, that's, I think, part of the definition. If you apply it to 1, you get 0. So it's perfectly well defined as an algebraic object, which means now we can exactly use these rules here and iterations of these rules to compute this project, this first thing here. So let's start with the last term. That vanishes because, you know, something which is constant is killed by a derivative. So that's gone. Let's look at this term. That's a product. So in principle, we would have to use the product, the Leibniz rule. But C just depends on set 3. That was the one of the postulates. If this Zn derivative falls on it, it vanishes. So this just leaves dzn pi x. And now this is the most interesting term. So again, so here we have a product of 4 terms. If this derivation falls on the first term, there's nothing. But then, of course, by combinatorics, you get 3 times the square times the derivative. So that's already not so bad, right? Because you see that slowly this prefactor is emerging. And now you have to understand what this does. But remember that this one had, was also satisfying a nice rule, pi times pi prime. Namely, it was an algebra endomorphism. So it was multiplicative. And in addition, it satisfied that on the Z3 variables, it was the identity on the Z3 variable. And so if we hit this term now with this, we have to apply the second set of rules. So let's again start with the product down here. So that's a product of 2 terms, so we can directly look here. But then on the C, because the C just depends on Z3, it's the identity. So down here we get C times gamma x star del Zn pi x. And on the first term, well, what happens there? So that's a product of 4 terms, 1, 2, 3, 4. So we use multiplicativity. There's nothing which happens on the Z3, and taking the square commutes because of multiplicativity, and of course this also commutes, so we get 3 times Z3 x star pi x squared plus this. And now by definition, or by the characterizing property of this transformation rule, this is just pi. And that was just, in our special case, the pi dot. And that means we get this equation. So that's a completely, so in a certain sense, in the end, the rigorous analysis or algebra is full of this type of arguments where you manipulate these kind of abstract objects, but with very precise rules, which all make perfectly sense. Question? Okay, so now essentially I would like you to remember this part here. Because now perhaps comes the important insight of how to find a good representation of the Malliavin derivative. And that, I will explain, connects to, for instance, controlled rough path, as we've seen also in yesterday's talk, afternoon talk, and model distributions, which are the PDE version of controlled rough path. So a good representation or robust representation of the Malliavin derivative. So recall that what we already know is that the Malliavin derivative satisfies this equation. And now if del psi were analytic, we learn from here, or the logical reverse from here, that we would get, we could treat the Malliavin derivative as a tangent vector and get the representation del pi is equal to the sum over all n. Let me now give this a different name, d pi n x, gamma x star pi x, at least in a formal way. Glancing at what we have here, we would get this representation for some d pi n x for some random d pi n x in our formal power series space with real coefficients. That would be too good, because del psi is not analytic, but it has a limited regularity. Namely order S. So instead of order infinity, it has order S if you want. So the intuition is that this identity does not survive as an exact identity, but as some kind of local approximation. So because of this reduced regularity, despite the fact that we gained a lot of regularity by going to the Malliavin derivative, it's far from being an analytic function, but we should hope to capitalize on the somewhat limited regularity. And so it is natural to expect that the Malliavin derivative of our model can be approximated by a truncated sum, and I should truncate it at the level 2 plus s, s being the regularity of del psi, 2 being what I gained from inverting the differential operator, d pi nx gamma x star del zn. I think I forgot the del zn here. Del zn pi x near 2 order 2 plus s near x. So that's the that's the analytic strategy to say this very, although still formal because the sum is infinite, this very nice algebraic but somewhat informal representation cannot be true because the element of the Cameron-Martin space just is of reduced regularity. It's not analytic, but it's not rough anymore. So therefore, we could hope that something like this approximately survives, and the best way to let something approximately survive is to say that it's, it locally survives. This is the reason why I introduced the base point x, because now I can say something along these lines. And so that, in fact, so that's exactly what we're going to prove. In fact, with the notation d gamma star x being this object here with the finite sum. And since s is between 0 and 1, it's just saying I look at all space-time multi-indices of length at most 2, so that contains 0, E0 up to ED, and EI plus EJ for space-like I and J's. So that's a kind of a finite number of multi-indices, so that's a finite sum. So if I define this, that's as a random endomorphism on this space. If I define it like this, then what we show is that if we look at the our Malliavin derivative, we subtract this object here, which is just kind of that same right-hand side written in a short way. We convolve it, because after all, those are distributions a priori, and we evaluate it at this variable x. Then this is big O of R2 plus S as R goes to 0. So indeed, we get locally around x an approximation of the order 2 plus S like this. And let me point out that, okay, so that's what kind of the main technical result is. Let me tell you how to think about it. So component-wise, this means that if you take the Malliavin derivative of a beta component, then here, in fact, you have a sum, beta gamma of pi x gamma. And it's this object which is nice. Of this order. So what does that mean? That means the Malliavin derivative is well described, or is described to order 2 plus S by the model itself. By this bag of functions we constructed, and the coefficients, so the jargon of regularity structures is modeled, and the coefficients are contained in this, are given by this matrix. Where now all the parameters matter. It matters that I can vary the base point x. It matters, of course, that I can vary the coefficients. And this object in the jargon of regularity structures can be kind of assimilated to what's called a model distribution. And this is, in the end, a little bit like Gubinelli's controlled rough path condition. Because it tells you that it's not possible to approximate your solution. In this case, the role of the solution is played by the Malliavin derivative. It's not possible to control this object just by polynomials up to a high order, but you have to enrich the space of polynomials, and you have to, you have to introduce coefficients, you have to modulate this space of enriched polynomials in order to get this good approximation property. So this is really, in a certain sense, it's saying that increments of this quantity are well approximated by increments of that quantity with coefficients which, as we will see, perhaps not, which satisfy their own kind of continuity condition, which slowly modulated coefficients. So that's the main insight that like in the solution theory of controlled rough path or regularity structures, you can treat the Malliavin derivative as a generic solution, and it has, in a certain sense, a similar type of approximation property. Okay, so that's the first main step, and so in a certain sense, I could have kind of postulated that right away, but it really is motivated by this geometric structure of thinking of the Malliavin derivative as being a tangent vector to the solution manifold, which tells you what type of structure this d gamma star should have. Let me write it down again. D pi n x gamma x star dzn. Okay, so what I want to, other questions? Yes?
The big O here, so if I'm not mistaken, the d gamma is random.
Yes.
So this big O, is it an almost sure, or is it in...
I haven't given you the rigorous statement. Well, I mean, in the end, what we prove is a kind of a quenched estimate, where we put our favorite LP norm here, and in that sense, we prove it in that sense. We always work, sorry, I'm confusing myself. So we always work with what we call annealed estimates. So the way we make things rigorous is via these types of annealed estimates, because as soon as we would like to express this in a pathwise way, we would run into the double logarithm problem, and we would lose kind of the clean scaling. So therefore, we work with this. And the nice thing is you never have to exit that framework. For the entire proof, you can stick to the annealed framework. More questions? Yes?
Can make sure that so for this approximation, as long as you can recognize the Malliavin calculus as a tangent vector, so it comes automatically?
Yes. So in a certain sense, I mean, what I'm doing here, I'm trying to kind of motivate the approach, and instead of kind of giving you right away this ansatz here, I try to motivate it, and I motivated it by saying the following. I forgot the analytic. So I'm thinking as follows. So the big gain of taking the Malliavin derivative is that you replace the noise by something much smoother. That was this gain of 3 derivatives, which I mentioned last time. Now we have to capitalize on this. That's the only way to kind of overcome the problem. So we have to capitalize on this. So now I'm being very bold and I'm saying, well, let's think of this as being actually infinitely smooth. And let's see what we gain there. Right? Because even if this thing is infinitely smooth, this solution is not infinitely smooth because these coefficients are rough. So the problem is that smoothness of the Cameron-Martin, even if our noise were, extremely regular, no, I shouldn't say that. So even if we could pick an extremely regular element del psi out of our Cameron-Martin space, we wouldn't gain the regularity we want because of this rough coefficient. This coefficient, many components of this coefficient are just distributions. So it's like solving kind of a heat equation with a rough potential. That's one of the problems some people talked about. So this you should think about a heat equation with a rough potential. So there is a problem. So the type of regularity that emerges can only be a subtle regularity. It can only be a regularity in the sense of controlled rough path, in the sense of model distributions. So now the idea to get the right ansatz for the model distribution is to say, well, let's now be extremely, let's be extremely rough and say, let's assume this is an analytic function. Then this del pi would be an element of the tangent space. And the tangent space we understand very well. And now we take this good understanding of the tangent space of the solution manifold and we say, well, now because our object is a little bit rougher than analytic, this can only survive approximately, so we truncate it. And that's exactly what we did here. More questions?
Could
Yes.
you remind me what is the meaning of the d pi x and to the power?
This here, that's just a notation. So for some random d pi n x, which is an object in this thing. This is just a notation, so I will explain in a second why it's a good notation. So you should think of this, before we had this dot here, which was also mostly just a notation. So this is a notation. So what I'm saying is, and we'll get back to this in a second, what I'm saying this, I can find these things actually in a unique way, such that this object satisfies this good approximation property. Yeah. So this d is not an operator like the del, but this is just a notation. Like this d is just a notation, but it's a good notation, as I hope to explain a little bit later. Right. So this is just notation. Notation, not an operator. So unlike del is not meant as an operation. More questions? Yes?
Like you just said that the Malliavin calculus making free degree of regularity. Can that free regularity be seen from this formula?
So remember that we just half an hour ago we went through these three cases, and we realized that for this very first multi-index we got the full benefit of the gain in regularity from going from psi to del psi. So we got the benefit that del pi 0 was in fact, as we would hope, 2 plus s. But then we already realized for the next multi-index this is no longer true. We just have a regularity which I think was h dot 2s. So we immediately lose the gain in regularity which comes from replacing psi by del psi. So in fact, the regularity that emerges is exactly this regularity which some of you are used to from rough path theory, controlled rough path theory, or from regularity structures. It's not it's not regularity as a kind of face value, but it's just you just can describe your objects are still extremely rough, but they are nevertheless, they're in a certain sense of a low complexity because they can be pretty well described by other rough objects. Yeah, so I think that's from a complexity theory point of view, that's one of the main benefits of regularity structures, that you say we're dealing with extremely rough objects. So in principle, your wavelet basis representation is by no means sparse, but now you find the right coordinates, you find the right basis, which is exactly given by these things. And if you use the right basis, an adapted basis to your problem, then things suddenly become sparse, right? That's the philosophy. And here you see one instance of it. More questions? Okay, so there are two things I want to convince you of to close the story of today, so to say. So remember that what I said a little bit before is that this map from pi to pi minus was not robust, unstable. And now I want to convince you that I get something that's stable on the level of the Malliavin derivative. And I haven't done that yet, but it's related to what we're doing here. So that's what I want to explain before the break, how what I just did here now exactly gives you this stable relationship between pi and pi minus on the level of the Malliavin derivative. Okay? So let's erase this here. So the first insight, so here I think I will return to the details tomorrow and just give you the rough outline today. So there is a next section which is called the structure of this somewhat ominous d gamma x star and its uniqueness. And so what I claim is that we have the following pleasing algebraic properties. So if we so remember that you should think about this as being an endomorphism, and there is something which almost looks like Leibniz rule, but it's slightly twisted if you want. So it looks like this. So the Leibniz rule would be if this kind of thing would not be there, but so it's kind of almost like a Leibniz rule. And I will say how to think about this in a second. And in a certain sense, what goes with it is that the 1 is annihilated. In fact, also the Z3 is annihilated. And in fact, even more so, all Zn's are annihilated unless the parabolic length of n is less than 2. So it's pretty sparse, this object, and these properties can be, in a certain sense, immediately read off from the derivation property of this here and the multiplicativity of that, and the fact that the sum is truncated. And so this motivates the notation, because in this sense, d gamma star x has the same algebraic properties as del gamma star x would have. So that's an exercise. Prove that, besides the last one, prove that del gamma x, which would be the Malliavin derivative of the change of base point transformation, exactly has these properties. So, so that motivates the definition that this d gamma object, it's not the derivative of anything, but it has some of the algebraic properties of a Malliavin derivative. And so that's the reason for using this notation. And now the claim is that what I wrote down here, what I'm erasing right now, so perhaps I shouldn't. And let's go back to this somewhat informal, non-annealed way of writing things. So since as long as rho is positive, all the objects are actually smooth, this here implies, or in fact is in a certain sense equivalent to saying that the object which we're monitoring here vanishes to second order in this base point x. And then there is an argument that this, together with these algebraic properties, tells you that this thing is uniquely determined. And I think I will give this next time. By del pi and the model and the usual base point transformation. So in a certain sense, we have a stable or well-defined map like this, and now I want to tell you that there is a stable map there. That's the last thing I'm going to write down for today. So that's the robust relation from del pi to del pi minus. And that follows essentially from one line, and I'm going to prove it probably next time. So, so the claim is that starting from here, so if this d gamma star x collects, if you want, the Gubinelli derivatives of del gamma, in this sense, then we have that the del pi minus can be expressed by the very same object in terms of pi x minus at the point x equal to 0. So this means we now get a representation of the Malliavin derivative of pi minus in some arbitrary point x in terms of the Cameron-Martin space thing. That's benign, we know it, and in terms of this object here, adjusted to the base point which is sitting there, which is determined from here. So that's exactly what I was trying to explain by the scheme. So we go from del pi to dx star, via this line. So as I explained, this line determines that object. And then in the second line, we go to del pi minus. And that, of course, defines something from del pi to del pi minus. And that's exactly the, that's in a certain sense mission accomplished, because you don't see any C. So hooray, the C is gone. So that's the in a certain sense completely algebraic realization which makes the thing work. That thanks to the Malliavin derivative, you find a stable representation of the object you're interested in. So in a certain sense, as I keep telling you, there is in infinite dimensional space, there are these two directions. There are kind of the expectations or averages. So this is where, for instance, E pi minus lives and C lives. That's, in a certain sense, a bad direction. But then there is the direction of the fluctuations. So that's where the del pi minus lives. And this one is good and stable. And this one is bad and unstable. And the original setup of the problem mixes these two directions. And now we kind of completely set them apart. So it's a little bit like in the Lyapunov-Schmidt reduction, when you kind of reduce everything to one kind of dangerous direction, and then there is, you put all the good stuff into the infinitely many other directions, and that's what we just did here. Some kind of Lyapunov-Schmidt reduction where we put kind of the stable part. We realize that kind of most of the problem is completely stable and robust. There are only kind of few dimensions, a finite number of dimensions that diverge where the counterterms diverge. That's the idea here. Okay, so I think that that in a certain sense is the main conceptual idea of how we use Malliavin calculus. So you see that it's probably somewhat different to the way you're used to using Malliavin calculus. So we're not using to prove that any density is regular, but we use it in this conceptual way of showing that on the fluctuation side, something is stable. We can rephrase the problem avoiding this divergent counterterm, avoiding these divergent constants. And what I want to do in the remainder, so I think I still have 3 hours, is now eventually tell you how to convert this into estimates, right? This is at this stage is just a story. So I think in the next step, I want to tell you, so in the end, in order to prove the estimates, we carry out an induction argument over multi-indices, and we have to come up with an order that's compatible with the algebraic structure of both this object and that object. So I want to tell you a bit about this. And then I want to tell you a bit about how to cope with the fact that we still have this mismatch of topologies. We have kind of the Hölder topology, and we have the L2-based topology, and how to use, in a certain sense, some Bezoff-type ideas to communicate between these two sides. But that would be then kind of really more of an analytic part. Since perhaps this would be too analytic, I certainly want to focus on this more combinatorial question of how to order the induction, what the right order of induction is to get the estimates. And I should stop here. Still time for questions?
Sorry, in my understanding, I'm concerned about the second line from above. From the last line and the second from. Yeah, it seems to me that delta pi minus something there is a formal power series inside the bracket. There is a formal power series.
Yeah.
And you could you explain the meaning of the d come to the power n of that power series?
The way to think about it is this. We're always thinking of X as being an element of this space, which in a certain sense is just a smart way of thinking about the coefficients which are in the space X, right? So this is kind of a grown-up way of thinking about your infinitely many coefficients, because there is an additional algebraic structure which you wouldn't see if you just think of them as a bunch of coefficients, namely that's multiplication, those are these kind of Leibniz type properties. So it's important to have this kind of vision at your disposal, right? So that's the first remark. Now, what is X? X is the space, as long as rho is positive, that's the space of smooth, random smooth space-time functions. So if I write, for instance, L pi, you may already wonder here, what does it mean? It just means applying this operator component-wise, right? Because this operator, the differential operator, just acts on the space X. It acts on the space of coefficients. So if you want the, I think I never really wrote it down, but what I mean is this, right? So it acts on the space of coefficients. That's the same thing, right? That's just another derivative. So that's the meaning of this. Does that explain it?
Yeah, but usually they come to some multi-index. So n is a multi-index?
N is always the space-time multi-index. So n consists of n0, n1, nd in n0, 1 plus d.
So it's a mixed partial derivative.
So, the way I would see this is that you're saying, so this is the classical way of expressing this condition. So here you're saying you have let's now think of a single coefficient, right? It has the same meaning if I say for every beta. So here I have a smooth function, and I'm saying that it vanishes to second order in the point X, because all its space-time derivatives up to order 2 vanish in this point. So if you want to picture, so here you have space-time, here's the point X, then you have a function which touches the axis very well, in the sense that the first term which you will see is cubic. That's what this condition means. More questions? Yes.
So you talk about the sparsity of coefficients.
Yes.
Can I say that you want the coefficient to be sparse because you want regularity?
I would put it the other way around. As I discussed here, and now it's gone, you have to face the fact that all the objects you're dealing with, at least in the limit when rho goes to 0, are rough. But you want to have an efficient description of these rough objects. They're not generic rough objects, but they have roughness has a certain structure. And sparsity means you want to describe them by as few, you want to have your basis set as small as possible. You want to have your neural network to be, as few neurons you need to encode the object you want to approximate. So that means here in this, that means when I'm saying that you should think of you should think of this, this approximation that the beta component of this object is approximated by star beta gamma p x gamma, right? That's what we're saying, that we can approximate this object we're interested in by a modulated linear combination of these objects. We want this sum to be as small as possible, right? Because that's valuable. If we manage to describe all these objects with a few things over there, that's sparsity. Then we're happy from an information theoretical point of view. So that means we want this thing here to vanish for as many gammas as possible. So we want this matrix, think of it as being a big matrix. We want to have this matrix to have as many zeros as possible. And it does have a lot of zeros because of these conditions here. That's what I mean by sparsity. More questions? Okay, I think it's lunchtime anyway.